which says Auckland, so there's been so I was at Cape Town until January last year, and December last year, and most of the work that I've been talking about was done there, and I'm continuing it at Auckland. So I want to be talking about a long research journey that I've followed to get to a point from asking a basic question on behavior, observed behavior, and why that is, to developing a system and how we think that system can inform the intelligent, good maintenance of distribution systems.
Sorry.
Was that you? Okay. So I'm going to give you a bit of background on behavior of leaks in distribution systems, talk about this device that we developed and show you some typical results of what we can do with those, and then talk about how we see we can apply this for better maintenance of distribution systems. So this equation you would all hopefully know, and this is the orifice equation. It's derived from the application of conservation of energy in this problem, where you have a hole in a container, and it just describes the conversion of potential pressure energy to kinetic energy. The important things in the equation is the flow rate Q and the pressure H. It's a function of the square root of the pressure. A leak is just an orifice, so we expect leaks to behave in the same way. However, when people started applying pressure management in distribution systems, which means having an isolated zone, reducing the pressure, there are many benefits to that, including lower breakage rates of your pipe and longer service life of your assets. But when they looked at what happens to leakage, they found that the orifice equation doesn't explain the behavior of the leakage with pressure. Oops, that's the wrong one. So what they'd adopted is just a power equation, and they're using this N1. N1 is a term used in the leakage practitioners community for an exponent, a leakage exponent, which should be 0.5 to theoretically, according to the orifice equation. But in practice, they measured a range from 0.4 to 3, which, because that's an exponent, makes a huge difference to the behavior of the system. And so my interest in this problem became, why is this happening? And we've done a lot of work, which I'll skip over, on understanding the different factors that apply to that, contribute to that. But the main factor, I don't know if anybody want to take a guess. Why are we seeing this high sensitivity of leakage to pressure compared to the theory? Okay, I'll release you. I've had a head start. So the main reason is that the orifice equation assumes the area of that orifice to be fixed. But in practice, the area of a leak varies with pressure. So there's two combinations. It's a velocity increase, which is proportional to square root of the pressure, and then you've got a bigger area and that combined effect. So we've done a lot of work in understanding that behavior. And what we found essentially is that leak areas vary linearly with pressure. And it doesn't matter what pipe material, diameter, stress conditions, type of leak, we always get this linear behavior. There are some examples, but there's some cases, but we can generally ignore them. This is just to show you some of our experimental results. So this is the area of a leak. That's the pressure head. You can see the data points there, and it fits nicely a linear function there. The two things that are important. The first is the initial area. That's the area when there's no pressure. And the second thing is the slope. Now, the slope is a function of the type of leak, the diameter of the pipe, the material used, the elasticity modulus, the size of the leak, and the wall thickness of the pipe. Those are the main parameters that causes it. So the idea is now, and just to show you some of our other experimental results, this is round holes. And so for round holes, you can see that the area is basically constant. It doesn't matter what the materials is. Those are two types of PVC pipes, HDPE and steel pipes. Round holes, the areas are very stable in all types of pipe materials. If you have longitudinal cracks, we see a much positive slope, so they expand significantly in area with pressure, depending on the type of material and leak. The exception there is steel pipes, which are very, at those small diameters, are very stable as well. And then circumferential cracks, we get normally a slightly negative slope there. So by understanding how different pipe materials behave and different crack types in different pipe materials and section properties behave, we can now develop the device, and this is what it looks like, the prototype, where the idea is to test a pipe in the field to see how its leakage behaves, responds to pressure, and then be able to calculate back and say, well, this is a longitudinal crack, and it's about 5 centimeters long, or whatever the case may be. So this is just in practice. This is some field tests we did in Cape Town. I'll just show you, that's about 300 kilos of device, and that's one of my students. He's finishing his master's now, if you want to play it. Trying. So about 300 kilograms, and the guys did a good job, or our designers, to make it really able to move from one spot to the next in the field. It's got a water tank, it's got a generator, it's got all the instrumentation built in. This is where we connect to a fire hydrant to connect it. So just to explain how it works, there's the water tank, there's a pump, there's some flow meters, some valves, and a pressure sensor. We would connect to a pipe in the field. The first thing we'll do is just to flush the pipe, just to get rid of any sediments, and then to fill our tank. We then isolate the pipe, we isolate all the users, and then isolate the valves on the main line. We would open this valve again then, because if any of the isolation valves are not sealing, we'll be able to see that there's a flow continuing to flow through that. And if we find that, we can characterize the size of that leak, and we can say which of the valves it is. So trying to get as much value from this test as we can. Then we would start pumping from our tank into the system. Because it's isolated, the flow that we measure there is equal to the leakage flow. And then by varying the pressure, the pump speed, we can have different pressures in that pipe, and we can calculate how the area then responds to pressure. So this is some results of field tests we did in Cape Town. You can see that the pressure there, this is 4.5 bar. We actually normally use lower pressures. We don't try and create new leaks, if at all possible. So you can see we reduced the pressure in steps, and each time the flow stabilized more or less, and we could get a flow pressure point, calculate the area from there, and these are the area versus pressure head, and you can see it's a nice linear function. And from this, we can see that the initial area, in other words, the area of that leak when there's no pressure on it, is 1.1 square millimeters, which is a real physical measure of the condition of that pipe. It just tells us something about the physical nature of what's happening there. And then the slope, that is characteristics of a longitudinal crack. It's a relatively large slope, and knowing the material, knowing the diameter and the class of the pipe, we can actually calculate what is the estimated length of that crack. So how do we see this working into a system for maintenance? I mean, the first point is that we can't get away from having to do maintenance in the field. You can never have a hands-off approach to a physical asset. You have to get there and you have to do maintenance and monitor it. So the idea of this system is to combine a lot of that work with these tests. So this is a device. It's linked, it's got a GPS unit in, and it's linked to the cloud-based server. Everything is done by the operators online. They run through a process. The data is all uploaded to the cloud, from where it can be analyzed later on. This is an app that we've developed that goes with the device, and the idea is that firstly we can schedule tests, so we can tell the operators where to go, we can tell them where the hydrant is and the valves are that they need to connect, and then secondly they can use this app to report any problems. So you've got your eyes and ears on the ground, they can take a picture of a wet spot or a problem or something that needs to be reported. And the third thing that they do is basic maintenance. If it's just replacing a small cover on a water meter, then they can do that in the field so that you do that basic maintenance. Part of that is also just opening and closing valves. You're supposed to exercise a valve once a year in a system. Just open and close it to make sure that it's not stuck and that it operates fine and so on. So this is all combined in that process. And then the data itself is analyzed there. There you can see a nice photograph with all your devices where they are, and then hopefully access them and see what's happening there. But having that information allows us to then characterize the different pipes and combine that information with existing information on history of pipe leaks, on age of pipes, on pressure in the system, and to be able to optimize the maintenance system for that. The idea would be that you do this once a year or once every 2 years. And what will that allow us to do is, because you find a leak on a pipe, that can be a very small leak, and it doesn't make sense to actually go and dig up the whole street to fix that leak. But if you can do that in 2 years' time, see that leak has actually grown, you can start a predictive process to see, well, this pipe is going to last another so many years, or we're going to have a problem this coming year, most likely a burst, and it's better to intervene now and have that pipe replaced or fixed. So just a summary of the application that we see for this. First, our device itself has some unique properties. We can identify very small leaks just based on that characteristic of that flow meter we've got on, and we know very little about what's called background leaks. Leaks less than 250 liters an hour. We know very little about what extent of that in the system. So I'm very keen to understand that better. Determine the characteristics of the leak, identify leaking valves, on-the-ground issue reporting, and some basic maintenance. Annual or biannual testing will allow us to follow the pipe deterioration, and then combine with existing data to come up with more intelligent decisions on when and how best to intervene to maintain the system. And then it also opens the ability to have agent-based maintenance, because you can actually track where people, your maintenance contractor is going, what they're doing, and really know that they're doing what they're supposed to be doing. And one of the ideas we've been playing with is remote intervention. So if you have a small rural village somewhere in Africa, and you have a local team that can actually do the field work, you're experts on the leakage monitoring and assessment, and can sit anywhere in the world, assess the information, and work with that local team on. And then if that's funded by a World Bank or some development bank, the idea is that doing a test like this can really help them to know that their assets has been looked after and their investment is protected. And finally, so we see this as a platform for other products. So we can start doing sampling of water quality. We can start adding functionality that if you do identify leak, to then locate where that leak is, and perhaps even in future do internal leak repairs right on the way. So that's it. Thank you very much.